The production of oil and gas is a complicated process that is abounding with challenges. Sand production in wells has plagued oil and gas companies for decades, and modern fracking practices have made sand production even more prevalent. The choke valve is designed to take the brunt of the pressure off of the line components, increasing their life and yielding significant benefits. By restricting the flow to a very small opening or orifice, choke valves reduce well pressure and control production rate, creating downstream or back pressure.
There are four main elements of concern in a choke valve:
inlet, outlet, trim, and throttling mechanism.
Choke valves are continuously subjected to pressure drops, corrosion, and erosion, which can cause expensive breakdowns. Erosion is the process of material destruction. A well stream typically consists of a mix between oil, gas, water, sand, and other various particles. When all of these elements hit the internal surface of the choke valve, it can cause erosion. The material properties of the choke valve and the impact velocity and the angle of the fluid particles affect the rate of erosion. Let's discuss how erosion affects several choke valves currently in use. The simplest choke valve is the positive type. The positive chokes contain built-in orifices called beans. To reduce erosion, these beans are often lined with tungsten carbide. However, these chokes are still susceptible to high rates of erosion.
An adjustable choke can compensate for some degree of wear, but a positive choke cannot. The pressure must be isolated so that the valve body can be opened and the bean removed. This is time-consuming and expensive.
For frequent flow regulation, an adjustable choke will work the best. One of the oldest designs is needle and seat. This valve has a tapered lead on its stem
To restrict the opening by closing the needle against the tapered seat.
The seat is typically threaded into the body, and the throttling is achieved by rotating the handle on its rising stem.
A narrow opening between the needle and the seat restricts the flow and causes an increase in fluid velocity, since velocity is a function of volume over the area. The seat surfaces act as restrictive devices, which subjects them to a higher friction and deterioration.
Multiple orifice valves, or disc-style choke valves, provide improved flow control and shutoff capability. When these openings are perfectly aligned, the flow rate is maximum. When these openings are offset by 90 degrees, it shuts down the flow completely.
Erosion is common around the edges of the holes. The high-velocity jets from the throttling ports flow into the valve outlet, resulting in high potential of valve body erosion. As the discs wear out, the valve's shutoff function could be lost.
Our next choke valve has fixed cage and internal plug. A stem connected to the cage allows the cage to be moved up and down by the rotation of the wheel, changing the size of the opening for the flow.
Inside the choke, fluid circulates in the annulus between the body and the cage.
The location of the cage openings forces the streams to collide in the middle. Impinging streams cause hydrostatic back pressure and allow using fluid energy against itself, resulting in minimal wear of valve material.
The cage and plug choke valves work best when the cage ports are fully open, which allows the high-velocity jets to be perpendicular to the valve axis. Otherwise, the jets are directed towards the valve outlet and cause its erosion over time.
Let's move on to the most advanced choke valve, the cage with external sleeve. This valve is best for high pressure drops and high sand concentration applications. Moving the seat to the outside where the fluid velocity is lower, reducing wear to the throttling surface and improving seat life. Reduction of valve outlet erosion is another important element of the external sleeve. It's achieved by directing the fluid exiting the throttling port into the valve trim and away from the valve outlet.
Let's compare erosion in the last two choke valves. Masterflow tested the effects of erosion at their state-of-the-art testing facility by placing 2 valves in a series, subjecting both to identical sand and flow rate conditions. Masterflow engineers encountered some interesting observations. As the fluid began to move towards the vena contracta, where the diameter of the stream is smallest, the fluid in the internal plug design accelerated in the cage port and directly impinged onto the exposed internal plug, resulting in an extensive material loss. The seat integrity of the internal plug was lost within 30 minutes. The external sleeve's seat feature was outside of the cage, away from the high-velocity turbulent fluid zone, so it lasted throughout the 10-hour test.
This valve's material loss was only 4.23 grams. In stark contrast, the internal plug design lost an astounding 12.75 grams. That's more than 3 times the material.
When the engineers compared the external sleeve to the internal plug, they observed that the plug lost 54 times more material. By placing the seat upstream of the throttling ports, the external sleeve valve was able to maintain shutoff capability by the end of testing and showed 20 times longer seat life than that of the external plug design. Also, the material loss of the outlet sleeve was 3.2 times higher, and the depth loss was 4 times larger in the internal plug valve.
This was explained by the CFD analysis that showed high-velocity fluid jets in the internal plug were directed into the outlet. By contrast, in the external sleeve valve, they were directed towards the valve trim, away from the outlet.
Now let's discuss the role of trim material in resisting erosion. For a long time, choke manufacturers selected their trim material from a nickel or cobalt binder tungsten carbide. To address both corrosion and erosion, carbide vendors began using a composite binder, a mix of cobalt, nickel, and chromium in a tungsten matrix. This material is traditionally referred to as tungsten carbide. In the tests conducted using the Masterflow erosion loop and several third-party labs, the trims made out of 5CB, a premium-grade tungsten carbide, demonstrated the highest erosion and corrosion resistance as well as toughness.
How better choke valves can affect your company's bottom line, you may ask? A Masterflow customer replaced the needle and seat choke valve at their shale gas site and shared the results. Before switching to the external sleeve choke valve, the company had to shut down production every 12 days to inspect or replace their choke valve. By utilizing Masterflow's external sleeve and cage design, they were able to extend this period to 80 days. At the same time, repairs-related expenses reduced by 65% using the external sleeve. And most importantly, the company was able to increase their production rate from 7 million standard cubic feet per day to 10, due to the improved erosion resistance by Masterflow's external sleeve and cage choke valve. Taking all of the factors into account, the producer was able to turn a $1,500 investment into a staggering $3.4 million of increased ROI. With less interruption in production and less time spent on costly maintenance, you can increase your profit exponentially. It's time to master the flow. Masterflow.